Okay, today in Chapter 12, we're going to be talking about chemical bonding. Now, our main idea between a chemical bond, it is just the attraction holding two atoms together. Now, while it is as simple as that, it does actually involve some complexity. Now, if it was on that first little thing, it says really involves isolated atoms, when it does involve isolated atoms, the bonds are a lot more predictable in how they behave. But as soon as we use two different atoms or two different atoms in general, we're going to have a lot more variety in the type of bonds we have. All right, but we will find that the chemical bonds that get formed and broken by chemical reactions do drastically change the chemical properties of the substances. Okay, so chemical bonds are simply the forces that hold atoms together, and there are two main types that we're going to be covering in this chapter. Ionic bonds, which are going to be attraction between cations and anions, or we could actually even say metals and nonmetals, because that's where we see them most of the time. Now, the metals do need to be ions, and we call them cations, and anions over here. And there is some variety to the cations. There are actual cations that are not metals that do actually make ionic bonds. But those are just attractions. They are very strong attractions, almost like magnets. But they can be very strong bonds. All right, the second type is covalent bonds, and these only happen between two nonmetals. There are a few exceptions, but for the most part it needs to be nonmetals. So on our periodic table, the yellow guys. All right, we're going to look first at the ionic bonds. Now, I did say metal and nonmetal, but it's better to call it cations and anions. That attraction between that positive and negative ions can be quite strong, and it needs to be done so in such a way that it neutralizes the charges. We already saw that when we came up with our ionic compounds. So if we were looking at something like sodium and sulfate, for instance, and wanted to make an ionic compound out of them, we would know, since sodium is always a positive one and sulfate's always a -2, sodium sulfate, there are two sodiums for every sulfate. So we already know that. On our ionic bonds, we just want to say that is because we want to neutralize the charge difference between the cations and the anions. Now that we've introduced this charge, we're going to see that the higher the charge between the cations and anions, the higher difference, the stronger the attraction is. So something like sodium sulfate has a very strong attraction because that -2 compared to sodium chloride, which is just positive and negative. And we do see that translates into things like melting point and boiling points. All right. Next thing we're going to look at is something that goes on with all of our metals and all of our nonmetals when they make the cations and anions. Technically, they turn into noble gases on their electron clouds. So sodium, normally, right up top, has an electron configuration of, starting with neon, just one electron in a 3s orbital. When it comes an ion, it loses that electron in that s orbital. We will sometimes actually see that written as 3s0, where they're stressing to you that the electron's left. Now on the other end, the anions, that is, chlorine, for instance, has electron configuration with 2 electrons in the s orbital and 5 in the p orbital, and as a negative it adds 1 more to that. And we actually show it completely filled. Now, technically, that second electron configuration with the 2s electrons and the 6 p's, that is argon, which is why they're showing this, just the brackets with argon. All right, but we're going to see that that happens all the time. The ions, when we make ionic bonds, typically form noble gases when they are doing their attractions. Okay, so various different ones and what they do. Now what we have here is, if you look at the periodic table, this is just that third row. So sodium, magnesium, then you skip to transition metals and go to aluminum. What they're showing is those outermost electrons are removed. So that one electron makes this a positive one, same electron configuration of neon. Magnesium loses 2 neon. Aluminum loses 3, both from the 2 electrons from the s orbital, 1 from the p, and it also looks like neon. Now, these aren't on that same row. They're on the previous row. They're on the second row, but they're anions, and they had to lose electrons. So oxygen loses, or no, sorry, oxygen gains electrons. So it had 2 electrons in the s orbital and 4 in the p. It gained 2 more, and now suddenly it looks just like neon. And same thing happened with fluoride when it gained the electrons. But we actually can see this by just looking at the periodic table. So our first row always loses 1 electron, becomes a positive 1. The second row loses 2. And when that goes back, like lithium goes back, it turns into helium on the electron cloud. Sodium looks like neon. If I'm at calcium, since it's going to lose 2, it goes back to argon. And then our nonmetals, they gain electrons to look just like that noble gas. So everything here, fluorine, chlorine, bromine, and iodine, gain 1 electron. Oxygen, sulfur, and selenium gain 2. Nitrogen and phosphorus gain 3. And carbon, if it does that, it gains 4 electrons. All right, so that's what they're showing with the electron configuration and how it changes as well. Okay, so which of these actually is the electron configuration of a bromine ion? So it does say, if it had just said bromine, we're going to start with argon, fill up our s orbital, fill up the d orbital, and get just 5 electrons in the p orbital. It would be this. This would be bromine by itself. Do watch out, see how that second one looks very similar, but it's got that 4. Remember, the d orbitals are a number below when we first filled up that row, because we're filling up the d orbital from the previous electron shell. All right, now, this doesn't say bromine. It wants to know bromine ion. And the most common bromine ion is Br-. It gains 1 more electron, will look just like krypton. So we just need to add 1 electron to this, making C our correct answer. That is Br-. And again, that one just has a 4 where it's not supposed to be. All right, on to our properties of our ionic compounds. For the most part, the melting points are very, very, very high. Some of the smallest ones are still in the 300 degrees Celsius. Sodium chloride, which we already introduced as a weak attraction, it has a melting point of 800, and actually I think it's 801 degrees Celsius. You can't even get that anywhere in your kitchen. Nobody has a stove that gets that hot. The solubility, we looked at them before. So the solubility of certain ones are much, much higher. And if you remember when we first introduced the solubility rules, we talked about how group 1s were almost always soluble. And that really is because of their size. The size of those ions are the biggest on the periodic table. So let me bring up the periodic table. These guys are the largest on the periodic table. And because of their size and that small charge, the attractions they're going to make with anything else are so weak that they typically fall apart a little bit easier. That helps make them soluble. So the strength of that lattice structure is what factors into the solubility. And that's also why, if you remember our exceptions with like chlorine and bromine and halogens, if you look, our exceptions were things like silver, which are going to be much, much smaller as cations, which is what's going on. That is why some of those are a lot less soluble. They're just going to make a very small, close bond. Okay, now we already said that our ratio of ions is based to get that charge neutralized. Like we said, sodium chloride was NaCl. But turns out that's not what the actual molecule looks like. There isn't an NaCl bond. In reality, Na in a crystal of salt has chlorines all around it. There's even one above it and below it. But what's going on is they are alternating. They actually form a cube, which is why, if you think about it, if you look at a salt, doesn't it kind of look like a cube? It actually is, and it's because of the arrangement of those little ions. It forms a crystal lattice. Now, all ionic compounds form crystal lattices. Some of them are a lot more complex, and they don't actually have nice little squares. So that actually introduces a whole realm of chemistry called inorganic chemistry, and it is study of crystals and such. Okay, on to covalent bonds. Technically speaking, a covalent bond is just where electrons shared. So where sodium chloride, Na plus and Cl minus, all the electrons, those outer electrons, ended up totally on the chlorine and none of them were on the sodium, and there's an attraction between that positive and negative ion. On hydrogen, instead of donating its electron, that hydrogen keeps its electron, this other hydrogen keeps its electron, and they actually get close enough that both these atoms think they own each of those electrons. So the hydrogen on the left thinks it has 2 electrons, and now it's like helium. And the hydrogen on the right also thinks it has 2, and it's just like helium. So that sharing is what makes a covalent bond. We typically, rather than drawing like this, we typically showed shared electrons with a single line. So if you think back to seeing times I've drawn nice little stick figures like that, that line was always showing a covalent bond. And it's always representing 2 electrons, and they're being shared by both those hydrogens. Alright, now before we actually do much with this, because we are going to learn how to draw these structures, we got to introduce a weird little feature that our atoms do. Most of the time, our bonds are going to be made by 2 different atoms. Atoms don't necessarily share electrons as fair. Like down here at the bottom, I have HF, hydrogen fluoride or hydrofluoric acid. Fluorine is very what we call electronegative. It's very, very, very much wants those electrons, which makes sense if you think about it. Where it's at in the periodic table, it's very small. It really wants to be like neon. So when it gets electron near it, it just takes it. It takes it from anywhere. And hydrogen probably wouldn't care if it loses an electron as much because it's way over here, like the group 1s. All of them like to give up electrons. And that's kind of what happens. The fluorine keeps the electrons mostly near it. We call this unequal sharing. It actually creates what we call a bond polarity. Part of that molecule will be slightly more electronegative than the other part. That's what these little symbols here. We're not saying that's positive because it's still a negative cloud. It's just not nearly as negative this side. So very negative side, not so negative side. Now that actually does affect chemical properties because if I have another HF in here, they're going to attract that more negative fluorine to that less negative hydrogen, and there's going to be some attractions there. These polar bonds create polar molecules, and polar molecules have stronger attractions to one another. Water, for instance, is a very polar molecule, which is why it has such high boiling points and melting points compared to other compounds its same size. Alright, so how do we know if there's unequal sharing? Pretty much any time there is 2 different atoms, there's going to be unequal sharing. Now, the nice thing is, on the periodic table there's a trend. The most electronegative one is up here at fluorine. Matter of fact, this next slide I have some values for it. Now, it's a weird scale. Starts at 0.7, goes up to 4. But that's the number they went with back when this was first developed. And it pretty much is a very even trend. There are some exceptions. But fortunately, since we're dealing mostly with covalent bonds when we talk about electronegativity, we're looking up here and how these vary. And generally speaking, the closer to fluorine you get, the more electronegative you are. Alright, now, what this does introduce is it helps chemists explain certain weird properties. So these numbers here, talking about the range of them and which one's more electronegative and such, where it really pays off is when we look at the difference between bonds. Like H2O, water, H and O, the difference is over 1 on the electronegativity differences. That's what makes that a very polar bond. It's a very big difference. Now once it gets up to about 1.8, you have an actual ionic bond. And what's interesting, even though HF is definitely a covalent bond, that difference being 1.9 helps explain why HF has some ionic type properties to it. It has almost ion forming properties. But it's still a covalent bond. Just this large difference just tells us that the molecule is very polar. Okay, let's see if we can actually rank this based on just the periodic table. So I'm going to bring up the periodic table here so we have it right next to it. Let me make it so we can see it. So nitrogen and phosphate, phosphorus, nitrogen and phosphorus. Between these two, which would be more electronegative? Well, the trend always goes up and to the right, so nitrogen. And then how about nitrogen or germanium? Germanium, which is down here. Still nitrogen, right? And then carbon or silicon. Carbon, silicon. Got to be carbon, right? Yeah. All right, now we're going to rank all these. Calcium, potassium, nitrogen, fluorine, silicon. We're going to actually put the highest first. Yeah, it doesn't really say. So if I were ranking these, the closest one to fluorine is fluorine, so that must be the highest, the largest. So I'm going to put it first. All right, after fluorine, in our nonmetals, we have nitrogen and silicon. The other two are actually metals. So which one of those is first? Nitrogen and then silicon. And then we have calcium and potassium, which are over in group 1 and group 2. Calcium's in group 2, potassium's in group 1. So calcium and then potassium. We are just ranking them based where they are on the periodic table. All right, on to something we can do with these and make our stick figures. We're going to introduce the concept of Lewis structures. Now, on ionic compounds, these are technically referred to more often as electron dot symbols. That's what I was doing with that sodium. When I actually take a sodium with one electron and turn it into a sodium ion, I take away that electron. Chlorine, for instance, on sodium chloride, has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. Remember how when we did our boxes in the last chapter, we didn't start pairing them up until we had to? We're doing the same thing for dots. So we're going to go around on 4 sides of the symbol before we start pairing things up. All right, but chlorine negative, which is what makes the ionic compound, just gets 1 more electron. So we're going to have 4 pairs on it. Now, when we actually draw a Lewis structure for sodium chloride, we really will just draw this sodium like that, and this chlorine like so, and we just draw them close together. There's no lines, because lines represent sharing, but we will end up drawing our electron dots almost like we would if they were noble gases, with just our dots. All right, now we're going to see something kind of neat. At least right now when we do ionic compounds, our metals that we use will always end up with just a positive charge and no dots whatsoever. They will always be the metal symbol with a charge, and that's it. The nonmetals are also going to end up with a charge, but we're going to end up with 8 dots on them, and that's just because they like to form those complete octets that we see on the noble gases. Now, later on we see there's exceptions to these, because we actually totally avoid doing Lewis symbols of anything in the transition metals. There's a reason for that we cover a little bit more in General Chemistry 1. Okay, so our Lewis structures are just showing how the electrons being transferred. When we get to our covalent bonds, they'll show how the bonds themselves are formed. So let's practice some of this. First with just those ionic compounds. So MgS and CaF2. All right, we want to look at the periodic table for Mg and see what kind of charge it would like to form. It's here in group 2, so it's going to form a positive 2. And sulfur, being in group 16, is going to form a negative 2. So Mg, I'm going to have a 2 plus with no dots. Sulfur, a 2 minus with 8 dots. And we draw them close together, that's magnesium sulfide, at least a Lewis structure. All right, looking at the periodic table, we're going to see that calcium is also in group 2, but fluorine's in group 17. So while this is a positive 2, fluorine's a -1. Now it will still have 8 dots around it. Now how do you think we're going to do that too? Well, we're actually going to draw 2 fluorines. Now I'm drawing it below and showing that they're both attracted, but that's part of that crystal structure we were alluding to earlier, the lattice. How they actually arrange in three-dimensional space gives that ionic compound its crystal. We're not really going to do that in this. We actually are just doing what we just did here. And it would have been perfectly fine for me to put the fluorines on one on either side of the calcium. So it'd be something more like this. Fluorine, calcium, fluorine. And keep it all in one straight line. Both are perfectly acceptable. Alright, the Lewis structures for covalent molecules are a little bit more involved. Now I know that you've probably seen water drawn like so. And that's kind of a Lewis structure. What's wrong with that particular one is technically the oxygen should have these little lone electrons on it. Even CO2, carbon dioxide, you've probably seen drawn like this, but we're going to see that the oxygens also have lone electrons on them. Alright, now rather than try to explain these two right now and why these are the proper answers, we're going to actually introduce some rules so we can get all of our Lewis structures properly. Alright, so very first thing you're going to do when you're actually coming up with a Lewis structure for a covalent molecule is determine the total number of electrons possible. Right up here we're going to do H2O, and then we're also going to go to CO2. So if I want to determine the total number of valence electrons possible, I know oxygen has 6 valence electrons and each of those hydrogens has 1, so that total molecule has 8 valence electrons. Still 6 for each of those carbons, 4 from the carbon, so 16 over here. Okay, very next thing we're going to do is we're going to attach the atoms together. And H2O, we're just going to put the O in between. And we're going to do the same thing with the CO2, but I'm just attaching them with single lines. So I'm making like single bonds. That's where we're going to start. We're not assuming we know there's double bonds or triple bonds. We're just putting out, we're just arranging the atoms in space and putting the attachment with a single bond. Now on that, I chose to put the oxygen in the middle on the first one simply because hydrogens are always on the outside. Now on the CO2, there really isn't necessarily a good reason right yet why I couldn't have done COO. But we are going to find that typically speaking, I give them to you like this, and I would have specified in the instructions that carbon was the central atom. Because until we actually build up a little bit more practice, there's not actually always a clear rule that says this atom should be in the middle. Alright, so we've arranged them in space. Step 3, we're going to arrange the remaining electrons to get 8 on anything other than hydrogen and just 2 electrons on hydrogen. And I typically go with the outside atoms first. So on H2O, I would look at this hydrogen, see, well, it sees those 2, it's fine, it's got 2 electrons, and so does that one. So those 4 electrons have taken up 4 of these, so I just need to put 4 more electrons on there, and if I put those on the oxygen, I have 8 electrons on the oxygen, and that fits this rule. And that's actually what we're going to do for our correct answer. So, got 2 electrons around each of those hydrogens, and 8 around the oxygen. Alright, now on the CO2, we have 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now the reason I did it that way is I made the outside atoms happy. Do you see how each of the oxygens now have 8 electrons? 2, 4, 6, 8, and 2, 4, 6, 8. So both outside oxygens have the 8. The carbon does not, though. Now, I can't add any more electrons because technically I've actually got all 16 electrons on that molecule now. So when we've run out of electrons and we need to make something in the middle happy, what we're going to do is grab electrons off one of those outer ones, and technically we're going to make them share. So those two became a second bond. And we're going to do it again with another pair over here. And now everything there has 8 electrons. The molecule is happy altogether. Alright, we're going to practice that on a few more. I got a lot more here, don't I? Alright, so right underneath these, I'm going to write down the number of valence electrons each of these atoms has. So hydrogens, being in group 1, all have just 1 valence electron. Chlorine has 7. I'm going to go ahead and put that 7 over here. So this molecule as a whole has 8 valence electrons. We're going to arrange it in space with an H attached to the chlorine. That takes care of 2. The hydrogen has 2, so I'm going to put the remaining 6 around the chlorine. And that brings the chlorine up to 8 valence electrons, or 8 electrons around it, so we are good with that structure. We've already done H2O, so I'm not going to bother to do it yet. Alright, but I will just write it here. That was one of the examples we did. And that was 6 valence electrons on there. That 6, and this is a 4, tells us that carbon monoxide has a CO bond. 2 electrons, 4, 5, 6, 7, 8, 9, 10. Alright, that gets all 10 electrons. The carbon is fine, but the oxygen is not. So we're going to do that same type of thing we did with the CO2 before. Remove 2, make them shared. Carbon still has 8 electrons, 2, 4, 6, 8. Oxygen still has 2, 4, 6. We're going to do that again. We're going to see that atoms, covalent bonds, can have up to triple bonds. And that is actually what carbon monoxide looks like. Has a triple bond between the carbon and the oxygen. Alright, phosphorus trichloride. We have a 5 there. And I'm going to arrange these in space. A little bit more complex here. And that's, let's see, 26, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Made the outside atoms get all 8 electrons before I actually added any to the central one. But that actually takes care of everything. We have 8 electrons on every single atom. That's an acceptable structure. Alright, nitrogen has 5 valence electrons, so this thing together has 10 altogether. So I have a nitrogen bonded to a nitrogen, 1, or 2, 4, 6, 8, 10. You notice how it looks just like what carbon monoxide looked like before? So we're going to take those 2 and those 2 and share them. Alright, our last one has probably the most electrons, because we got 6 electrons from sulfur, 6 from oxygen, so we got a grand total of 30 valence electrons. Then this -2 means we add 2 more. So this whole thing has 32 valence electrons. Alright, sulfur is in the middle. You're going to find out for all of our polyatomic ions, the oxygens are always on the outside. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Got 8 on every single one of them. Now that particular one, because of that 2 minus there, we need to put this entire thing in brackets with that 2 minus there to show its charge. All right. We are going to see that triple bonds are the most we can get in covalence. We can get singles, doubles, and triples. There are some weird exceptions later on where you have an odd number of electrons in there, but everything we see in intro and even general chemistry are just double, triple, and single bonds. The bond strength goes up with the number of electrons in there. A triple bond is much, much stronger than a single bond. And the length is actually the opposite. The single bonds are the longest, and the triple bonds are the shortest. When we actually put a whole molecule together, we're going to see that this helps us predict the shape of the molecule based on a few cool things. So it says to look at formaldehyde. I meant to have a picture here of it. But the actual chemical structure of formaldehyde almost looks like a triangle. And it is flat. If it lays down flat, it is a perfectly flat molecule. Now, those three groups are technically trying to get as far away from each other as possible. So if we treated them all as the exact same, the bond angles are dead on 120 degrees. Because that's how geometry works. They get as far away from each other as possible. But since that bond has more electrons in it, and oxygen is bigger, it pushes on these a little bit more. So this is probably closer to 121. Doesn't push on a lot. Think about it as an umbrella in heavy rain. You wouldn't notice the umbrella collapsing, but it probably is ever so slightly collapsing some. And that's what happened with the molecules. When you get more and more electrons on one side, it actually pushes down on the others. Alright, but that is what we're going to call a molecular structure. Now, typically when we draw Lewis structures, we're always going to end up with a two-dimensional structure. And that makes sense because you're drawing on paper. But we're going to see that molecules actually have a three-dimensional shape. Sometimes they are flat like this. This molecule is perfectly flat, but other ones are not. Water, for instance, we drew it nice and straight. We actually ended up drawing it like this. Yeah, if it was flat on paper, we would actually see a bend to it. And this is about 105 degrees. And that's because these electrons, which are up here, are pushing down on it. They're actually making that molecule bend. They actually occupy space. Alright, so where do we come up with this? Well, there's this theory, valence shell electron pair repulsion theory, that predicts the shape. Now, all it does is it basically says you have a central atom and you put things around it. Like water had two X groups. Now, if it was just two bonding groups, they would get as far away from each other as possible and be at 180 degrees. But water doesn't have just two things around it. It's bonded to two things. But it also have two electron pairs. So they actually say E's for that. And all four of those things are trying to get as far away from each other as possible. Now, that particular structure is one that actually ends up coming out of the paper at you. So what we could say is we're going to say these two guys are coming up at you, and these two are going back. And it forms a weird little four-sided dice looking thing, like if you've ever seen Dungeons and Dragons thing. So it's these are kind of connected. Those are connected, and of course back in there. But it's like a weird dice that's got like the four sides to it. Call it a tetrahedral. But it's got a shape to it. Now, your book has a better drawing of it. That's what they're showing here with the four different groups coming off of it. On water, two of those are hydrogen and two of those are electron pairs. But they're getting away from each other as far as possible. Hard to draw on paper, which is why we don't even try. All we're always going to do is if you see four regions, regardless of what they are, if they're bonds or electron pairs, it's going to have that tetrahedral arrangement. All right, now that's how we're going to do to predict our geometry. We are going to use the Lewis structure first. So CO2, we've already done it, actually looks like so when the Lewis structure is all done. CO2 has just two things coming off that central atom. They're going to get as far away from each other as possible. They fit the geometry of linear. So this molecule actually is. That is a 180-degree molecule. We actually do say it's linear in shape. But we're going to count a bond, whether it's a double bond or a single bond, as a bonding thing. And then electron pairs also as its own thing. But it has to be electron pairs. Okay, so that's our three main geometries. Got two things coming off a central atom, three things, or four things. Okay, when we actually give a full molecule, we're going to have to keep in mind that the electrons alter the name of the shape, but get it in that same category. What I mean by that, NH3 has a Lewis structure that looks like so when it's all done. CH4 has a very similar looking structure. Instead of a lone pair, it's got that pair of electrons shared with a hydrogen. Well, technically speaking, the bonding groups are all around the same. They're all about 109.5 because there's four groups. These are a little bit smaller because those electrons push more. But for the most part, the bond angles are about the same. But we only call this one tetrahedral, because that family name, the family names, come about when the things in those the four regions are occupied with atoms. So those are all atoms, so we call that tetrahedral. This one's in that same family, but we actually call it trigonal pyramid. And that really is because those electrons are pushing down on these. It's like taking that tetrahedral and cutting the top off. So it's a misshaped pyramid. And those names are right along here. So we have linear, and that is just a single atom with two groups. And we have trigonal planar, which is a single atom with three groups. But if you take one of them and turn it into an electron pair, we have a shape we just call bent. This one's bent. And then these guys, you have four groups. X. Ooh. I hit my coffee cup. This one's tetrahedral. Three groups. E for the electron pair. That was the trigonal pyramid. I'm going to move up here. I can't write at the bottom of this page. Two X's and two E's. This was water. And it's just called bent. Bent. Book says V-shape as well, but I don't really ever see many people call it that. I think they do the V-shape or bent so to try to distinguish these two. But your book's the only one I've ever seen that does it that way. Most call them both bent or V-shaped. Alright, but to do that, you have to do the Lewis structure first. So what I mean by that, let's actually do one of these. So silicon tetrachloride. So got 4 valence electrons from a silicon and 7 from a chlorine. So I have a grand total of 32 valence electrons. I'm going to put silicon in the middle and surround it with the chlorines. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Alright, so that would be my structure. Got octet around everything, so 8 electrons of everything. My silicon has 4 things coming off of it. I could say it is an AAX4, has 4 groups. That is tetrahedral. Alright, phosphorus trichloride. Phosphorus has 5 valence electrons. Each of those chlorines has 7. This has 26 valence electrons. And if you flip back a couple slides, we did this as one of our examples. Octet all the way around on everything. So this one has 3 groups and an electron pair. That is trigonal pyramid. And our last one, CO3. Got 4 from the carbon, 6 from each oxygen. That would give me 28 electrons, and that gives me 30. That 2 minus adds 2 more to it. So, carbon surrounded by 3 oxygens. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26. I didn't count something right. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I like that better. And what did I do here? 6 times 3 is 18. And then 4 more is 22, and 2 more is 24. Alright. Helps to have known these ahead of time, because then I catch my mistake that way. Alright, so if we did see that, we have all the oxygens have an octet, but the carbon does not. So we're just going to arbitrarily decide to take one of these pairs of electrons and share it with the carbon. So one oxygen gets a double bond, the other 2 are just single bonds, and we are going to finish this up with a -2. Alright, but that central carbon has 3 groups coming off of it. So its shape is related to that AX3 aspect, which is trigonal planar. Now this does technically end up looking a little bit more like that formaldehyde in the flat triangular shape. But you don't have to redraw them. This shape was drawn based on knowing that structure. It's perfectly fine to leave the Lewis structure like a 2-dimensional drawing. Alright, so let's see if we can do one of these. We actually have done H2O already. And if you don't remember, the Lewis structure ended up looking like so. So what's its shape? Now, a lot of people end up drawing it and immediately go for linear. There's no way this is linear. And it's because those 2 electrons take up space. This has 2 bonding groups and 2 electron pairs. This is bent. And we introduced NH3 in the geometry, but let's actually do it real quick. So 5 valence electrons and 1 from each hydrogen. Arranging these in space, I have 8 total valence electrons. 2, 4, 6, 8. That is what NH3 looks like. It has 3 bonding groups and 1 electron pair. So it is trigonal pyramid. Alright. The polarity of a molecule deals with the sum of the polar bonds. What do I mean by that? Technically speaking, on carbon dioxide, the bonds themselves are polar because oxygen takes those electrons away from carbon. So if we do these little Debye things, that bond looks like so. And so does this one. But think of this as like a tug of war. Since that's a linear molecule, that pull is going against each other. This side's pulling the same part as this side. They cancel each other out. So they're not even there. They're going to help with reactions, but the actual molecules themselves are not attracted to one another. Therefore, this molecule is what we call nonpolar. Alright, let's look at another one that's got a similar shape. Or at least on Lewis structures it has a similar shape. And that's H2O. And if I draw it like this, you might think it's the same thing. But remember how that was bent? Well, H and O are unequally shared. And there's no way this is going to actually cancel each other out because of that bend. That becomes a polar molecule because of that shape. That bond polarity is not canceled out. So to actually decide if a molecule itself is polar, you have to do the Lewis structure first, and then you're looking for that symmetry aspect of it. Most linear molecules, when the two groups are the same thing, are nonpolar. And that's actually true for any of the families. So if I have a trigonal planar molecule where everything is the same, actually I'm going to do it much more general. Got a central atom and these are all the same. That's going to be nonpolar because they all end up canceling out. And same as the tetrahedral ones. If they're all the same, they cancel each other out. So what you need to make something polar is to have different groups. So even like that tetrahedral, remember how we introduced the first one with just CH and H's? Well, if I change one of these to fluorine, suddenly there's no more symmetry to the molecule, and this molecule is actually polar. That carbon fluoride bond is a lot more electronegative towards the fluorine than the rest of the molecule, and that makes the whole molecule polar. Alright, now we can actually see the effects of polarity on physical properties. They really will actually arrange themselves in magnetic fields or electrical fields based on that charge. But more importantly, what we see going on is when they are around each other, there's attractions between the positive and negative parts of the molecules. And those attractions keep the boiling points and melting points high. So all polar molecules have higher boiling points and melting points than nonpolar molecules. Alright. Now that just summarizes what we just said. Alright, now got plenty of practice on this and on the worksheets. So, and the book will definitely help with more practice. And to be quite honest, practice makes perfect here is a very true rule, because if you get really comfortable with Lewis structures, it really makes this test quick.